Hello students, welcome to Mr. Goddard's review of oscillations, waves, and sounds. So I'm not going to read every single slide here to you. I'm not going to reteach everything, just go over the highlights, remind you about some of the uh, variables and the concepts, some of the relationships, and just pretty much hit the high points here. So let's get going on oscillations. So if you remember, an oscillation is anything that's moving back and forth, up and down, left and right, over and over again. So if we have a graph of that, then the period, which we use a capital letter T to represent, would be the time period between maybe two successive peaks, or maybe between two troughs. The frequency is the inverse of that, and we measure frequency in hertz, or 1/seconds. If you're looking at a graph, this one's a little bit more of a standard graph. The amplitude is the maximum displacement from equilibrium. So from what I would call the baseline all the way up to a peak, or from the baseline down to a trough. You can see also the sketch there of the time period and then the relationship with that with the frequency. On your AP formula chart, that formula is sort of hidden. That is this one right here with the F equals 1/T. Right in the middle it's got a 2 pi over omega, but that's fine. T is obviously the time, measured in seconds. F is frequency, measured in hertz. 2 pi is just that, a constant. And omega is the angular frequency. Sometimes it's called the angular velocity. It's measured in radians per second. So two things that we can do with this formula. One is just sort of ignore the middle one for a little bit and say the left hand side equals the right hand side, showing that time period is 1 over the frequency, or if you want to flip that around, frequency is 1 over the time period. Or we could focus just on the middle and the right hand side and do sort of a cross multiply butterfly effect here. Omega equals 2 pi f. This is a way of converting from hertz to radians per second, or radians per second back to hertz, if you would need to do that. Anytime we have oscillatory motion, then it's going to be, the graph of that motion is going to be sinusoidal. And we said that simple harmonic motion is the cause. What simple harmonic motion means, anytime that you have what's called a linear restoring force, which means that the force is directly proportional to displacement from equilibrium, or the force is equal to some number times the displacement x. Alright, so the examples that we talked about were horizontal springs, vertical springs, and pendulums for small angles. Just a slightly different graph of a mass moving back and forth, left and right. In this case, the amplitude would be, as always, the distance from the baseline there to the maximum displacement to the right, or the maximum displacement to the left. You've got turning points here and there. If you graph it, we mentioned that the position graph is sinusoidal, the velocity graph is sinusoidal of oscillating motion, as is the acceleration. They're all sinusoidal. They're not all sine graphs, but traditionally what we're going to do is the position graph is going to start off displaced at its maximum amplitude, and then we ran through this example plotting its position through over the course of time. And then the velocity graph, we just sort of asked ourselves, when is the velocity going to be 0? Well, it's going to be 0 at the very top, at the very bottom, then again at the top. So we plugged in 0 here, 0 here, and 0 at the end. And then we said, all right, it's going downward here, so it's going to have negative velocity. Upward up here, it's going to have positive velocity. That negative velocity is going to have its maximum value, so to speak. It's going to be the most negative right as it's passing through equilibrium, because before that it's speeding up, and then after that it's going to be slowing down because the spring's going to be pulling up. So the maximum negative velocity is at the equilibrium point. The maximum positive velocity is also at the equilibrium point. And the acceleration, one way that we talked about acceleration, said, all right, acceleration corresponds to the force which is causing the acceleration. So when is the force going to be negative? When is the net force rather going to be negative or positive? When the ball's up here at the very top, then gravity is pulling it down. The spring is pushing it down, so it has the most negative force, most negative acceleration. When the ball is all the way down here at the bottom, it's going to have the most positive net force because it's about to be yanked up here. So that's how we drew this. And then a couple of times the net force is going to be 0, and that's right as it's passing through the equilibrium because it's not being pushed or pulled by that spring. So that's when the net force is 0, that's when the acceleration is 0. Another way that we could arrive at these same conclusions was through the kinematic relationships. We knew that if you're looking at a graph of position, then the slopes would be the velocity. And if you're looking at a velocity versus time graph, the slopes are the acceleration, the values of the slopes rather. So for instance, when the slope of a tangent line here on the velocity graph is 0, that's going to correspond to a 0 value on the acceleration graph. You can see if we drew little sort of toothpick segments all along here about the slope, they'd all be positive, so that's why you've got all positive values here, and then 0 here would correspond to a 0 on the acceleration. So if we wanted to actually write out the formulas, the position, the x of t, is a cosine 2 pi ft, the velocity is negative v max sine 2 pi ft, and acceleration is negative a max cosine 2 pi ft. Something I've seen a lot of students get confused about, and they might try to take advantage of this on the AP test, is that frequency and velocity are not the same thing. I mean, it should sort of tip you off. I mean, they're different words. But just because you've got high frequency doesn't mean you have high velocity. In fact, now you might, and you probably, if you do have high frequency, something's going back and forth really, really quickly. But the thing is, the velocity will change. If we look down here at the very last thing, velocity is constantly changing. That's what this graph back here represents. There's sometimes when the velocity is 0, even if it's just momentarily. The frequency, however, will not change. It's if something is moving back and forth, back and forth. Now, eventually, if it stops moving altogether, then the frequency would be different. But the frequency is going to be constant. It's the velocity which will be changing. So you can read through that more if you need to. This was just as a reminder that if you knew the amplitude and frequency, you pretty much could plug that into these formulas and get all three of them. This is what's going to be on your AP formula chart. The x position at any given time can be calculated if you know the amplitude. This is just the cosine function. This little side note, I probably should put this in here. This is in radian mode. 2 pi is just the constant, f is the frequency in hertz, and time is time. So for instance, if you want to know what is the position of a pendulum or a spring at 5 seconds, you plug in 5. What's the frequency? 1,000 hertz. I don't know. So you plug in 1,000. Well, what's the maximum amplitude? You plug that in, and you could then get where this particle would be, where this pendulum would be, where this spring would be, or what have you. All right, if you remember energy of something in simple harmonic motion, well, it's all pretty much the same. We know that the total energy of the system is never going to change. It's just some of that potential energy, well, the potential energy will turn into kinetic energy, and kinetic energy will turn back into potential, and they'll be going back and forth, back and forth. It actually forms a sinusoidal graph as well. But at any given time, if you add them up, it's going to equal the same amount here. Unless there is, energy lost due to thermal effects, in which case it's going to be going down slowly or quickly, I guess. So in this case, as it's going through the equilibrium point, that's when the kinetic energy was the highest and potential energy was the lowest. But then when the spring was all the way squished over here, then potential energy was the highest and kinetic energy was at its lowest. All right, so this was just some formulas related to that. Then these were the formulas that related the frequency and period of pendulums and springs. What's on your AP formula chart is this formula right here, that the time period of a spring, of the mass on a spring, is equal to 2 pi square root of m over k. K is the spring constant, m is the mass, and as I mentioned a second ago, t is the time period. This is what's the time period of something moving back and forth on a spring. For a pendulum, that was t of p. This is also on the AP formula chart. L is the length of the pendulum, and g is the acceleration due to gravity. So this depends on what planet you're on. And then if you take those formulas and take their reciprocals, you could get the frequency. And we just did some analysis. What if K increases or decreases, and how does that affect frequency, and so on and so forth. Damped oscillation is any time that you have friction, which is pretty much every single time. Sometimes maybe it's the drag force due to air resistance or whatever. And what you're going to get is you're going to have a sinusoidal graph. However, it will be bounded by an exponential decrease. And so we saw that up there. There's lots of things we could say about the time constant and things like that, but that's all written down in your book. You've got different types of damping. Now, mathematically, the oscillation never ceases. However, eventually it would be too small for you to even recognize. We also talked about driven oscillations and resonance. Driven oscillation is when you are periodically hitting or adding an external force. I sometimes would say adding energy to the system. In any oscillating system, there is the natural frequency, F naught, where it naturally wants to, I'd say resonate, but naturally wants to operate at. And then you've got your driving frequency, which is how often you are applying a force. And if we look at this response curve, we can see around the natural frequency, if we apply an external frequency near that, then we are going to get a high amplitude response. And then you can look at different systems, lightly damped versus heavily damped systems. So resonance occurs if you're driving it, if your external force is near that natural frequency, and you get that high amplitude response. We saw that later, what this actually means in terms of the physical processes when it comes to waves and sound waves and standing waves. And this means that you have a standing wave and you're just constantly adding energy to it at that same frequency. And we'll talk about that here in a minute or two.